Really excited to have Jeff here today. If you haven't met Jeff, he's a wealth of knowledge, especially in the optical gas realm. So with that, I think I'll just let you take it away.
All right. Yeah. Again, thank you very much for the invitation and for the opportunity to speak to everybody today about our company and our products, and specifically on optical gas imaging camera systems. A company out of Texas came to me and said, hey, I want to be able to see if there's a way to detect gas leaks. This was a company that was about an 80-year-old oil and gas company that they were in the midstream kind of portion of the industry, and mainly laid pipe basically for natural gas pipelines. And it was in the late 90s, they had an explosion and they had a serious accident, and there was fatality in that accident. And so the ownership of the company, one of the guys reached out to me and said, we got to figure out a way other than sniffers. Is there a way to detect these types of gas leaks? Is there a way with infrared to visualize it? And with infrared, the idea that they came to me is that the gas was cold, okay, and that you would be able to see it by its temperature difference, like if the gas was escaping, if you had a crack or a small pinhole. It'd come out of the pipe somehow. It would cool the pipe. You'd be able to scan the pipe, especially above ground pipe, and be able to actually visualize the temperature difference, and that will give you an indication. But I had already been doing that for about 10 years, trying it in the downstream area with refineries and petrochemical plants, and everybody else said, no, that's not the way to do it. So now let's forward. So I joined this company called Sierra-Olympia Technologies in 2017. I had started another company, and then we sold that company to another defense contractor, and joined this company. And the president and I have known each other for 30 years. And they said, all right, we want to build a really badass new technology OGI camera. So let's figure out how to do that. And so that's what we set out to do in 2017. So becomes the result of that. And what was happening at that time in the infrared world was new detector material that's called hot midwave. It stands for high operating temperature. All the GF320s operate at cryogenic temperatures in order to make the infrared sensor active to infrared energy, and what's referred to as the mid-wavelength of 3 to 5 microns. And then we put this filter in there that narrows that down to 3.2 to 3.4 microns, and that's where there's about 22 different hydrocarbon gases that emit precisely at that wavelength, and that is why the cameras can visualize the gas, okay? The second element of it, though, is what's called the delta T. You do need a temperature difference. If you get at thermal equilibrium, if they were literally at the same exact temperatures, then you wouldn't actually be able to visualize the gas. It would be too difficult because the background and the gas would all be at the exact same temperature. So on a day like this, if you were to do your OGI, you'd want to do it on a nice, bright, sunny day where you have a higher delta T between the gas temperature and your background. In this case, we'll call the cement our background. So the better that is, the greater that is, the easier it is to be able to visualize and detect any of these gas leaks. So with that cooled technology operating at cryogenic temperature, 77 degrees Kelvin, we had to use a big, what's called a rotary cooler, or a lot of people call it a closed cycle Stirling engine. And a simpler word for it is a little refrigerator. And it's, when you power it, it's just a closed cycle system. It has a little piston basically that expands and contracts the gas through an orifice and continuously supercools it. And then once it gets to its operating temperature, in this case, minus 77 degrees Kelvin for the older systems, then it just stabilizes at that and keeps the camera running as long as you have power to it. So in this camera, what we did is at that time, the military, again, and we were trying to devise a new technology and sensors that will allow the temperatures to be, the sensor to operate at a higher operating temperature, not as low. And the purpose of that was to be able to reduce size, weight, and power of the system. And because you didn't have to work as hard to cool the detector so cold. So what we were able to do is develop a technology, again, that we call a hot midway sensor. And it operates at 150 degrees Kelvin instead of 77 degrees. So that's minus 200 versus minus 100 degrees C. And so with that, we were able to take, I'll say the GF320, it's about an 8 or 9 inch camera. And it's yay big, you know, like this. And we were able to reduce this down to the fact that it now fits in the palm of your hand. Okay. And in this particular case, it weighs about 452 grams. And so it's super, super lightweight. But we increase the reliability of the camera as well. What's called the cooler, the device that actually cools the sensor. In those older systems, they only are rated to about 8,000 to about 9,000 operating hours, and then you have to service them. These run about 16,000 to 25,000 hours. So we actually got better performance, better reliability out of it. And the other thing is we even got better sensitivity. And what happened was back then, the sensors were using what's called quarter VGA resolution, 320 by 256. And what we did is we introduced the first VGA resolution sensor of 640 by 512. That equates to 3.5 times more pixels. So when you see the imagery from this OGI camera, it looks a lot clearer, a lot sharper. It's much easier for the operator to be able to visualize that leak and see where it's coming from. Our idea, because of our background, as I just explained to you, was in the UAV market. What we saw with the Quad OOOa regulations that had just come out during that period of time, it's going to be about scanning more equipment and doing it more frequently. Our idea at that time is, hey, UAVs were just really starting to come into some type of acceptance. And the whole thing about that technology is, that's what our president came up with. I have to give him credit for this. Every gram counts because it relates directly to flight time. And back then, you remember the M600, you know, that flew for like 17 minutes, right? And that thing was huge, right? And, you know, from the very first moment we approached the multi-rotor guys, they said, oh, it's got to weigh really, it's got to be lightweight, you know, in order to not compromise flight time. And so that is why we ended up building the camera the way that it is. So we took what was normally an 8-pound camera to reduce that down to a half-pound camera, basically. And it was a game changer. Now, if you see up here, what we produce is just the component. We don't produce an end solution. We rely on companies like Frontier and other technology partners who take our component. They have to integrate it and make it into a finished product that you see here. Now, we work really hard for our technology partners to make that happen. We have a lot of tremendous engineering support to guide them and you know, create what we were also thinking in our vision as well, but somebody else actually has to do that. So everything that we do is just an open frame infrared camera that has to be integrated into an enclosure, a pan-tilt positioner, a gimbal, handheld portable camera. And that's why I just was showing you, this is one of our partners on the handheld side. This is a company called Champion X. They're based out of the Houston, Texas area. They're pretty well known in the chemicals business, and they developed really the first new OGI handheld, you know, camera in the last 20 years, because we here at Optical was basically have that market for a long time. So this was built and purpose built under the new regulations for Quad OOOOc and Appendix K. So it has every tool and every function in it that meets what those requirements are going forward. So it was a unique place and time to build a product. And it again uses what's referred to as the Ventus OGI. So here's the evolution, the 210, the 300, and now the 350. And then there's now about 27 other UAV platforms that integrates the Ventus OGI onto it. Frontier has many of those. This is a company called Inspired Flight. This is a US-based company. This is another company called Free Fly out of Washington State. This is called the Astro. This is called Vision Aerial, which is a Texas-based company. We're working with these guys. I was just telling the story for y'all that haven't been here. This is a company called Census, and they're out of Daytona Beach, Florida. And they actually have a VTOL platform of vertical takeoff and landing. So it takes off vertically, then is an aircraft. And so for long endurance, we envision like pipeline type applications, things like that, along with fixed wing, type of aircraft is a good use case for it. Just a couple of other things on the controller itself. There's some particular operational modes, and just to throw out what they mean, if you ever hear them. Besides that gas enhancement mode, the camera, when it comes on, it's in a state which is called automatic gain and level control. It automatically sets the brightness and contrast for the temperature range span. So it's almost always in a really nice, perfect looking image. You don't have to do a lot on the controller. Okay. This AGC ROI, what that means, it's a region of interest. You can actually set within the image, essentially where you want that to occur. If you want it to calculate it on the whole image, 75% of the image, 50% of the image, or upper half, lower half. The reason for doing upper and lower half, if I was looking and I had my sky as my background, I didn't want to have that integrated because it's so much colder. Then I could basically put the region of interest on the bottom half of the image, and it will only adjust it to the actual equipment that you would be imaging. That's the purpose of it. Another thing called flat field correction. When the camera turns on, it actually self-calibrates itself. It's a really nice thing. If I remove the lens, there's what's called a black body calibration flag. What it does is after the camera cools down, which takes about 3 to 4 minutes, so you do have to wait for the camera to cool down before it's operational. And typically on the screen, you'll see a bunch of vertical bars, and then all of a sudden, as the camera gets cooled and it becomes operational, then the image starts to appear. And then you'll hear, if you could hear it, it's usually you can't, you'll hear a little click. And that click means the flag has gone down momentarily and just compensates for any offset or drift in the detectors, and it makes the image perfect. Then you don't ever have to do it again. If you want to, there is a manual adjustment where you can just say, I want to do a flat field correction. They think they call it a 1 point, and it just clicks it down again. If for some reason you had been operating the camera continuously for 24 hours, you might want to do it again. But when you're doing it from an airborne platform, you're only going to be flying maybe 45 minutes at the most. Okay. The cameras also have digital zoom capability, 1x, 2x, 3x, 4x. You can manually adjust brightness and contrast. There is image stabilization and roll stabilization. That's electronic. But because like the M350 and the 300 and most of these other platforms, they're so stable, you normally don't want to turn those on because it does do some averaging of frames. That way, if you're moving fast, for instance, and you're trying to image, it can kind of break up or smear the image because it's slowing down the frame rate, basically. So you don't normally want to turn those on, and many of the integrators don't put these in. You can do other things like sharpen, reduce noise, and do what's called strength and blending, which is, again, just enhancements that you're doing on the image. Here again is the optical gas gem mode. Again, that again is referred to as the gas enhancement mode. There's two different lenses which are available with the camera. Most everybody uses this one. It's called the 25 millimeter field or focal length lens. It has a 22-degree horizontal field of view. Most everybody is flying these platforms from 75 feet to about 150 feet AGL generally, but certainly with the 25 millimeter, you could easily use it to find leads up. I usually tell people about 400 feet AGL for the max that we can fly anyway. Beyond that, then you could consider switching to the 50 millimeter lens, and it is interchangeable. And you don't have to do any recalibration, which is really nice. We've been doing testing up to about 1,200 feet AGL. We have another lens coming out that we're going to be flying on the Air Ranger, by the way, which is going to be 100 millimeter. We're going to be flying that at 3,500 feet AGL. And but you got to remember, we're looking at pipeline leaks, which are under pressure. And typically, those are pretty. When there's a leak, it's a base. These are in the kilograms. We're not looking for LDAR leaks, at 22 grams per hour or something like that. So the next thing is a lot of people ask about on these cameras, does it meet Quad OA, Quad OOOOc, and now Appendix K minimum detection and visualization capability? And the answer is absolutely yes. We use third parties to verify that. And so with the Quad OA, it was originally 60 grams per hour. It was a 50-50 mixture between methane and propane. And so that equates to about 10,000 ppm. So that's a pretty small leak. The new regulations now broke it up. The EPA decided to actually focus on individual gases. And the three control gases they use is methane, and that is at 19 grams per hour. For propane, it's 22 grams per hour. And for butane, it's 29 grams per hour. There's still many other gases that the OGI cameras, they can visualize. As I said, there's 19 other ones that this one does. Cameras do not speciate the gas. They all essentially look the same. But there are very unique characteristics or signatures to certain gases. Some are heavier, some are lighter. As you do a lot of this, you can actually, in many cases, some of the operators and even I today can actually say, even if I didn't know what it is, I could kind of have a pretty good educated guess, because some gases are very heavy and they stay very low near the ground. Methane, of course, is lighter than air, so it goes straight up, right? And even if it's a heavy wind like it gets up here or in the Permian, where we have a lot of wind as well in Texas, then, it's still, even though it'll bend it over, it still won't sink. It's always either going horizontal or it's rising. So you can usually tell what some of the gases are. So diesels, the gasolines, all of those are super heavy. They stay very, very low to the ground. So they're easy to determine what they are. But every customer, when they're doing optical gas imaging, even in the downstream in a refinery or petrochemical plant, they know what gases are flowing through their system in which unit. So they know if there's a leak in this area, it is probably, this gas, and most of the time it's indicated right on the piping or something like that. In Appendix K, they're actually calling out now that that either the end user, the operator, the manufacturer like us, or service companies, they would like for people to now establish what is called the operating index and the operating envelope of when you're using an OGI camera, especially if you're going to use it as the alternate work system to method 21 of using snippers. You actually have to validate how you're doing that. And so what that kind of looks like is something like this. So when we went through our most recent testing to validate for Appendix K, we decided to follow what the EPA was doing and kind of show people what this might look like. I think we're the very first company in the United States to do this. And so what we did is we established these characteristics of OGI performance audits, necessary supplies, site facility inspections, record keeping, and field conditions. So I'm going to take this past this. So what we did, and nobody's ever done this that I know of before, because everybody asked you this, but nobody has the information. We kind of now have it. So what we did is we established these test parameters, this operating envelope test parameters, when we validated that our camera can meet the minimum detection for LDAR inspections. Now remember, this is for LDAR inspections. Many companies are not doing the testing to this level. Many companies are just still today find the leak and fix the leak. And they are not trying to actually measure how small or necessarily how big it is. What they're really trying to do is find them and fix them and reduce them, right? Because if an auditor comes in from the State Air Quality Board or from the EPA and finds that leak before you find it, that is when they can fine you. And they start the fine, as probably everybody in here knows, they start the fine from the last time they did their inspection. So if that was a year ago, that starts from a year ago to this point in time. They assume it's been leaking that entire time. And that's why the operators get these fines of hundreds of thousands, if not, a few $1 million. And then everybody has to sit around the table and negotiate, what they're actually going to pay. So in this particular case, what we did is we just said, okay, to find these minimum leaks, we're going to establish and do our testing under these conditions. So we picked wind speeds from 0 to 10 meters per second. So that's up to about 17 miles per hour. Distances from 0 to 25 meters. So that's about 75 feet. Delta T's from 0 to 15 degrees centigrade. We tried the 2 different lenses. We used different operating camera modes and then using digital zoom. Okay. So all of these things can have an effect on how far and how small of a leak that you can see. And so on any given day, one of the easiest and fastest things that we've always done is you can buy these little porta-gas cylinders. When it was quad OOOa, it was a mixture of the methane and propane. It was actually calibrated and it had a regulator at 60 grams per hour. You could get a dual one, which would take it down to 6 grams per hour. You set that bottle out there and you start at 10 feet away and you just walk backwards until you can no longer see the gas leak. And on that given day, that means under those climatic conditions of wind, right? Overcast, sunny, it could be snowing, sleeting, whatever it is that you're operating that particular day, that establishes what your operating envelope is. But nobody ever really wrote that down or did anything. They just used that as the test. Now the EPA and your air quality boards are asking people to define this so that they know that when the operator goes out to do an LDAR inspection, they know what the limitations of their product is. And this goes for aerial, goes for handheld, it goes for fixed mounted continuous monitoring, whatever OGI camera, whatever application. If it's on a robot, any of those things, you have to establish how and when you're going to be able to use that camera and successfully, if needed, you would be able to find a 22 gram per hour methane leak. That's the whole purpose of it. So then what we did in our testing, just a real quick snapshot, we created a whole bunch of videos. We sent it out to a bunch of different senior operators, and they had to basically grade the observability of the leak and the probability of detection. And so that's what we did to establish, again, what we call an observability and probability of detection index, and which means from a senior operator to a junior operator, how likely it is that all of these people agree at being able to see the leak, right? And then what we did is we created hundreds of graphs and plots about changing the distance, the wind speed, and the delta T. And the end result of that came out exactly kind of what we thought it was going to be. The general trends that we found: as the temperature differential increases, the observability increases. Just what I said earlier, right? As wind speed increases, the observability decreases because it disperses the gas, right? And as distance increases, observability decreases. But you can correct for these kinds of things because you can use longer, narrower field of view or more telephoto optics. So if you're just using the one control, meaning like a 25 millimeter, these rules, would exist at some degree, but you can always affect these by some of the things that you can change by the modes that you operate the camera in. And that's what we show here. This is where we use the standard AGC mode. That's what the image looked like. Cloggy, notice the same image, but in Cloggy, it looks a lot better because there's more contrast and edge adjustment. And then when you use the GEM mode, the gas enhancement mode, it's even more visible. And what we found is the GEM mode, in many cases, in some cases, allowed us to visualize that same leak twice as far as it would if there was no GEM mode on. So very, very interesting findings that kind of came out of that we kind of knew, but we never had it down on paper. And so this is now a pretty extensive document. So with that is all I had. Does anybody have any questions? And then I think we'll do a little demo. That sound what you'd like to do?
Perfect.
All right. So anybody have any questions about anything?